Hi folks, Mr. Long here. I'm just going to do a screencast of your polynomial functions test. What I'm going to do is I'll do a screen recording for any mastery questions because those are things that you're going to want to redo. So again, this is the polynomial functions one. So this way you can look at your rubric, identify the questions that you didn't do correct, and then you can rewind, review, go through the solution. So here we go. I'm going to go through the solutions on this assessment. So to begin with, so this question was about determining the definition of the derivative, what we say from first principles or from the difference quotient. So to start any question like this, one of the things that you're going to need to do is to start by writing the difference quotient, and that's this part right here. That equation is the difference quotient. Okay, the next thing you're going to want to do, now I do it off to the right, I go through and evaluate, I state f at x, that's what's given there, that's f at x. Then I evaluate f at x plus h, right? In f at x plus h, I replace all of the x's with x plus h. Let me get that a little bit thinner there. So that's everywhere where I see an x, I replace it with x plus h. So at those two locations where I would normally have an x. And then I'm going to do the expanding, so x plus h squared. So that's going to be 2 times h times x, 2hx. Then I would times that by the 3 to get 6xh. So that's 6xh right there. Then I would, I have to multiply this through the brackets. So that's hard to see because it's not zoomed in enough, but it's 4 times x, 4 times h. So it's negative 4x, negative 4h. And finally, the plus 1 is a constant. It doesn't change. Last thing I need to do, when I look back at my formula, I need to do f at x plus h minus f at x. That's the rise, okay, and rise over run. So now I have to subtract those. So it's kind of easy because I'm subtracting f at x plus h minus f at x. So I start here at f at x plus h and I minus f at x. So what I'm looking for is what are things that are the same, and then I can divide them out. So 3x squared, or subtract them out, 3x squared. And then negative 4x, subtract negative 4x is 0. And then 1 subtract 1 is 0. So anything that's the same in both equations will be 0. So the only thing that we're left with, or the only terms that we're left with, is the 6xh. Oh, there's a 3h squared, which I forgot in there. And then a negative 4h. Okay, so those are the terms that are left over. So I can take that, and this is, oh sorry, that's the subtraction there. And then I can take this value right here, and I can replace f at x plus h minus f at x. So I go over to here, and I in fact do replace it. For me, my next step is, some people like to common factor to do these solutions. Oh, by the way, notice you need limit notation the whole way down. You can't drop the limit notation until you're not dividing by 0 anymore. Okay, so I do this, and now I'm dividing out the h's. That h divides out with that h. One of those h squareds divides out with that h there, and that h divides out with that h. Okay, I guess I should mention that, so when we do this, we're breaking down our fraction separately into those 3 separate fractions. So what's left over? Well, oh, right away I can see that I got rid of that, that, and that. I no longer have h, I'm no longer dividing by 0. So now I don't need to have a limit that approaches 0. I can actually get to 0. So we write h equals 0. And I'm left with 6x, 6x, 3h, 3h, h is 0, and then subtract 4. Okay, so that's done. So then I write simplified form there, 6x minus 4, which you probably, based on the rules that you've learned, The derivative of 3x squared is 6x. The derivative of minus 4x is minus 4. So we've got our answer there. Okay, next one is derivative rules. So for this, there's a lot of simplification required, and often before you actually, this doesn't zoom enough, before you actually do your derivatives. So in the first one, the derivative 3x to the fourth is very easy to get. That's 4 times 3 is 12x cubed. The derivative of 1 is very easy. It's a constant, so it's 0. Now that I'm not going to do the derivative right away. First I'm going to write it as a power function, which is 3x to the negative 2. So what I do is I come over here and I write this as, so I take my 3 and I place it outside. I take my 3 and I place it outside the d by dx, because 3 multiples, and then I have x to the negative 2 in the brackets. So this means I haven't taken the derivative yet, but I'm going to, because I had to simplify first. Then I take this negative 4 and I leave it outside of the brackets, and then inside the brackets I have to rewrite x, square root of x to the 5th, as a rational exponent, a fractional exponent. So that's going to be x to the 5 over 2 because it's the square root. Okay, in my next step, I do the derivative for those ones that I haven't done yet. So I need to do the 12x cubed I already had. Then I need to do the derivative of, so this is going to be 3 multiplied by negative 2, that's negative 6. And then I reduce the exponent by 1, that gives me negative 3. In the next one, and I'm going to take 5 over 2 and multiply that by negative 4. 5 times 4 is 20. 20 divided by that 2 is 10. So minus 10. And then 5 over 2 minus 1. Well, that's the same as 5 over 2 minus 2 over 2, which is 3 over 2. You'll notice that in the solutions, in the instructions, it says you must simplify to positive exponents and radicals. So no fractional exponents. So that means x is being repeatedly divided by 3. So in our final answer, which is over here in this box, it's 6 over x cubed. Subtract 6 over x cubed. Then 3 over 2 means an exponent of 3 and square root. So minus 10 cube root of x squared. Or sorry, square root of x cubed. Next one, let's look at this one here. So for this one, again, I'm looking for some division. First things first, we're going to do some dividing. And so we're going to simplify with that. So I have, over here, I have this division to do right here. 6x to the 1/3, because cube root is x to the 1/3. And then x squared over here is x to the 6 over 3 here. Why did I do that? To get a common denominator, so I could subtract. Okay, and then on the other side, it's just x to the 5th divided by x squared, which we can see right here. X to the 5th divided by x squared. I still haven't differentiated yet. I'm still simplifying. So when I divide and I have the same base, I subtract exponents. So that's 1/3 minus 6/3. So that becomes 6x to the negative 5 over 3. And then I need to take 5 and subtract 2. And that gives me 3. 5 subtract 2 is 3. So now this right here is a derivative, or sorry, an original function that I can differentiate quite easily. So in terms of what we do, we always take the exponent and multiply by the coefficient. So I have negative 5/3 multiplied by 6. So negative 5 multiplied by 6 is negative 30. Negative 30 divided by 3 is negative 10. Got that. And then what I have to do is negative 5 over 3 minus 3 over 3. Okay, so I subtract 1. 3 over 3 is 1. So that's negative 8/3. Okay, we know that since the exponent is negative, that means it's in the denominator. It involves division. We also know that the 8 represents the exponent and 3 represents the root. So negative 10 over the cube root of x to the 8th. And then this part is very easy. That's x cubed, and the derivative of x cubed is 3x squared. That's your overall derivative. Okay, so last one. This is just a really nasty one that you have to expand through the brackets. So you're going to expand there and expand there. But before you do that, you need to represent it with a rational exponent, a fractional exponent, and or a negative exponent. So what we can see here is I've already shown you this. So we're taking the x to the negative 3 and we're distributing it into the brackets. Okay, we're expanding brackets. So when I do that, I add exponents if the bases are the same. So let's come over to here and look at this. So the first thing I need to do is I'm going to add negative 3 and negative 1/2. Sorry, you'll hear a dog barking. That would be our Labrador or St. Bernard. I'm not sure which one. Oh no, it's our St. Bernard. So now I have to subtract these exponents. And so I represent, this is negative 3, so I'm going to keep the same denominator. The way to represent 3 with halves is 6 halves. And then on the other side, it's actually quite easy. It's x to the 4th multiplied by x to the negative 3. Well, negative 3 plus 4. Okay, so now what I'm going to do is I'll draw a black, and I apologize how small this is. It won't zoom any bigger. I keep trying to zoom bigger. Oh, you can see the little word maximum. So you can see here that when I take my negative 6 over 2 and I add negative 1/2, I get negative 7 halves plus x. And now that is ready to be differentiated because it looks like a power function. That's why the power rule works, or it only works for power functions. So I have to bring the negative 7 over 2 down to the front, multiply it by that coefficient of 1, even though there's not a 1 there. We can write in a 1 if we want. 1 times negative 7 over 2 is negative 7 over 2. Negative 7 over 2 minus 1, exponent minus 1 is negative 9 over 2, because it's 2 halves. And then the derivative of x is just 1. The last thing we need to do is, and that would be the Labrador barking. The last thing we need to do is represent it with a radical function. And because we don't want fractional exponents. So we see that that's a negative. That means it's repeated division, so it has to be in the denominator, and the 2 indicates square root. Okay, so that's why we see here there's no mark there, which indicates square root, the common root. Okay, so that is your algebraic rules, the power rule with all the different simplifications. So what about graphical derivatives? So that's the next question. What is the derivative of the given graph? So the graph shown in red here, and this is the original function. What I'm going to do in green is draw the tangent slope function, the first derivative. So what we need to do here is I'm just going to go through and get a little bit, get a blue and make it a little bit thicker maybe. And what I would encourage you to do is really, when you're doing a question like this, draw a series of tangents. Right? Draw a series of tangents. And this will help you, like within each segment, draw a tangent between each max and min, and then to the left and to the right, near the end behavior. So if I look, the first thing I always want to do is identify those areas that have a maximum or a minimum. Okay, so very clearly, right there, the tangent slope is 0. So the derivative value is 0. That's f prime of x in green. Here, I have a horizontal tangent, therefore the tangent slope is 0. Here, there's also a horizontal tangent, therefore the tangent slope is 0. So what do we have then? We have a function here. And then what do I need to do? So I've got the zeros, right? I've got all the zeros plotted. Then I simply need to plot on, and I should use a different color than that, sorry. Maybe black will work. And then this right here, if I look at that tangent, slope is positive. It's up here. And it's going to be positive all the way to there, which is right there, right? And then the tangent in between this location and this location, the slope is always negative. So it looks like so. The tangent slope at this location right here is 0. And then the tangent slope between this location and this location is positive. Again, we have a tangent slope of 0 at x equals 4, and then it bounces and goes like so because the slope is positive. So I'll highlight in black now. Our derivative function, our tangent slope function looks like that. Okay, and there is a special feature here. That is a stationary point, okay, a point where the slope is 0 and the concavity is 0. And when that occurs on the original function, the first derivative, the tangent slope function, has a double x-intercept. Okay, so that is your graph of the tangent slope function. Okay, the last question was a tangent question. And I'll highlight this tangent question. This is a type 2 question. And in our type 2 questions, we are given the tangent slope, but we're not given the value or the location of the tangent. So I'm just going to do a little rough sketch here of say, a tangent curve or tangent line. So say that this is our point of tangency here, and that point of tangency has coordinates of a, comma, f at a. In other words, the x value is a, and the y value is f at a. So our tangent at that location might look something like that. And the slope of that tangent is f prime at a. Okay. That's the tangent slope, f prime at a. So we have 3 pieces of information we need to get the equation of that tangent. We need to know the x value at the point of tangency, the y value at the point of tangency, and the slope at the point of tangency. If we know those 3 things, we can create an equation of the tangent. So what is this? The slope is 11. So automatically that is f prime at a. Okay, and by the way, there's the equation for the tangent. That is on your formula sheet though. So f prime at a equals 11. We know that because the slope of the tangent is 11. We need to figure out a and f at a. I always start by writing the original function on the left and the tangent slope function or the derivative on the right. And then I use whichever one I need to use. So since I know what f prime at a is, that means that I can figure out what x is, or the a value, right? So I know I can replace f prime at x with 11, and that will equal 8x minus 5. So I know the slope of the tangent, which is the value, the y value of the derivative of the tangent slope function, and I solve for x. Okay, so f prime at a, x, or f prime at a is 11. Solve that equation, I get x equals 2. So what does that mean? That the slope of this curve is 11 when x equals 2. And that gives us our a value. Okay, once we have our a value, let's come back over here. So now we know that a equals 2. We also know that f prime at a is 11. What do we need to figure out? F at a. So I'm just going to substitute that 2 into the original function. F at a is just f at 2. And I take the original f at x function. Everywhere where I saw an x, I replace it with 2. F at a then equals 10. So the point of tangency is 2, comma, 10. That's the point of tangency. And the slope of the tangent is 11, okay, which is f prime at a. So now I rewrite the tangent equation, and f prime at a is the slope, that's 11. The a value is 2, that's the x value at the point of tangency. F at a is the y value at the point of tangency, and that's 10. This is a perfectly fine final answer. I'm okay with that. In fact, I like it because it gives me an ordered pair that's on the line, 2, comma 10, and the slope is 11. Or you can expand out that 11 bracket x minus 2 and simplify into y equals mx plus b form, which, which I did for you here. Maybe. Right there. 11x minus 12. And that could be your final answer, or 11 bracket x minus 2 plus 10. Okay, folks, hope this helps. Again, you want to look at your rubric and make sure that you understand what mistake you've made, what question you made it on. Go back over the video. I would, if you need to do derivative practice, I would go back and look in your notes and redo the review, or go back to Google Classroom to look at the review. Okay, so I hope that helps, and have yourself a good day.